You know when you're looking at a chart and the line is just shooting upward and you think, awesome, things are growing? Well, as we're going to see in today's explainer, not all growth is created equal. We're about to decode the actual anatomy of growth by looking closely at the hidden math behind increasing functions. Seriously, think about this for a second. If two graphs are both moving up, like tracking from left to right on the page, how can they possibly be telling completely different stories about what's actually happening to the data? Going up isn't just one single, simple type of movement. The way a line travels upwards actually hides a whole narrative about speed, momentum, and future trajectory. Okay, let's dive right into this. Here's our roadmap. First, we're defining strictly increasing functions. Then, we'll look at the role of concavity before breaking down three specific scenarios: accelerating, decelerating, and maintaining a constant linear path. And finally, we'll wrap it all up with a quick summary. All right, starting things off with section 1, defining strictly increasing functions, our baseline. So a strictly increasing function is basically just a mathematical function where the y value consistently goes up as the x value increases across a given domain. For this explainer, we're exclusively looking at scenarios where there's constant forward momentum. Think of it like a car that is always in drive. The position is always increasing, and the car literally never goes in reverse. Which brings us to the golden rule. The absolute crucial point here is that the first derivative, which we represent as f prime of x, must be greater than 0. In calculus, you know that first derivative tells us the rate of change. So when it's strictly greater than 0, that's the universal mathematical rule for forward upward motion. Regardless of anything else going on, our graph is climbing. Moving on to section 2. Let's talk about the role of concavity, which is really the secret ingredient here. Let's contrast these two core concepts side by side, because this is where it gets fun. As we just saw, the first derivative, f prime of x being greater than 0, determines our direction. It tells us, hey, we're moving forward. It's exactly like looking at the speedometer of your car and seeing a positive number. But the second derivative, represented by f double prime of x, is our secret ingredient. It dictates the concavity, or the actual physical shape of the graph. It tells us how we're moving forward. You can think of the second derivative exactly like the gas pedal in that car. So what happens when we step on that pedal? That's section 3, accelerating, concave up graphs. Now, what's really interesting about this visual is how the curve behaves as we track along it. Look closely at that shape. It bends upwards, right? Almost like a ramp that's getting steeper and steeper as you move along the x-axis. The math behind this visual tells a very specific, aggressive story. Not only is the first derivative positive, but the second derivative is positive as well. So let's summarize exactly what this means. The curve bends upwards. The first derivative is positive, meaning, yup, we're growing. But crucially, that second derivative is also positive. F double prime of x is greater than 0. Going back to our car metaphor, a positive second derivative means we are pressing our foot hard on the gas pedal. The speed isn't just constant, the upward momentum is actually accelerating. The rate of growth itself is growing. But what about the opposite? Let's hit section 4. Decelerating, concave down graphs. Okay, focus your attention on this next curve. Notice how the graph is definitely still going up. Our golden rule is still in play. F prime of x is greater than 0, but the physical shape is entirely different from the last one. It bends downward. The steepness is fading, and the line is starting to visually plateau. It's still growing, for sure, but the rate of that growth is shrinking. Why? Because the second derivative, f double prime of x, is now less than 0. And this brilliantly illustrates the stark difference between these two types of growth when you place them right side by side. On the left with a positive second derivative, we're basically mashing the gas pedal. On the right with a negative second derivative, we're letting off the gas. The car is still rolling forward, right? The numbers are technically still going up, but that explosive energy is gone. We're effectively decelerating. Which leads us to our third scenario in section 5, the constant linear path, or setting cruise control. Take a look at this one. What you're seeing here is a perfectly straight diagonal line. It doesn't bow upward like a ramp, and it definitely doesn't arc downward like a dome. It's just completely straight. Mathematically speaking, it represents a state that is neither concave up nor concave down. Let's outline the specifics of this steady state. The graph is perfectly linear. It is, of course, still increasing, so our first derivative definitely remains positive. But because it has absolutely no bend, again, neither concave up nor concave down, the second derivative is exactly 0. When f double prime of x equals 0, our metaphorical car is officially on cruise control. We've got constant steady growth without a single drop of acceleration or deceleration.
All right, let's tie it all together in Section 6, summarizing the 3 types of growth.
Here's our ultimate cheat sheet. Let's walk through this carefully row by row. In every single case we looked at today, the first derivative is greater than 0, meaning the line is moving up. That foundation never changes. But look at that second derivative column. It changes the entire story of the graph. If it's greater than 0, we get a concave up shape, which tells a story of accelerating growth. If it's less than 0, we get a concave down shape, meaning the growth is decelerating. And if it's exactly 0, the line is straight, meaning our growth is entirely constant. The second derivative really is the absolute key, the single variable that dictates the true nature of the growth.
So, I want to leave you with this thought. The next time you see a chart showing growth, whether you're looking at a company's financial profits, population statistics, or literally any real-world data at all, are you just going to be satisfied seeing a line going up, or will you stop, apply these calculus principles, and ask, wait, is this growth accelerating, decelerating, or just coasting? Understanding that hidden math completely changes how you interpret the world around you. Thanks so much for joining me for this explainer, and keep asking those deeper questions.